So thank you for staying tuned and for staying on board on our lecture on our journey through stochastic processes. And I have to say I'm really happy about the way that we cooperate so far. It's a wonderful experience to meet you each week in the online classroom and to discuss the problems with you and the sheets and the exercises. And I see that you are really throwing yourself into the subject, and just as I do, and I think it's really a wonderful joint experience that we're having together. So thank you so far. So the next segment will conclude, I think, basically our introduction into the long-term behavior of Markov chains, and gradually we will also come to an end with this part on Markov chains. Namely, finally, we will discuss what is called the Ergodic Theorem and also the property of mixing of Markov chains. This is the question to what extent you can actually observe that on the long run the Markov chain attains the equilibrium distribution in a way that either involves taking averages along the pathwise behavior of the Markov chain. That's the case of the Ergodic theorem, when the statement basically is that the time averaged sequence of observations of a Markov chain through an observable will converge to the spatial average taken on the collection of all states when we work out this average with respect to the equilibrium distribution. So time average on the long run equals spatial average. That's the core conclusion of the Ergodic theorem for Markov chains. And we will discuss this, and you will see that it's surprisingly easy to prove this. And the second phenomenon of long-term behavior that we will ultimately consider is the question of mixing of Markov chains. This is the case when the Markov chain approaches the equilibrium distribution, even if we do not take time averages, just if we evaluate the Markov chain at time points which lie very much in the future. This will be a simplified, this will be a conclusion which will be more difficult to obtain, but it will be more powerful because it will allow us to evaluate basically the equilibrium distribution only by taking samples from the Markov chain at large times, and we don't have to take the whole time average observation of the Markov process, which involves many time steps. And this will be true for certain Markov chains which are basically aperiodic. That will be the basic condition under which the conclusion is true. And this is on the one hand conceptually very interesting and nice, and on the other hand it can also be used in a constructive manner in order to sample from complicated distributions on certain discrete, say, configuration spaces, as they appear, for instance, in the case of equilibrium statistical mechanics, by designing a Markov chain which is tuned in such a fashion that it actually is a mixing Markov chain which approaches this given distribution, which is then a posteriori considered to be an equilibrium distribution. The famous example where you apply this idea is the Ising Model of magnetism, which is probably the most classical model in equilibrium statistical mechanics. And when you do the thermodynamic limit, if you like, or even close to the thermodynamic limit, this is such a complicated distribution that it's very difficult to take samples from it. And so you design a Markov chain which will do the job for you, which you initiate at any initial position, and then you let it run for a long time, and then you, by this abstract theorem, you know that it is close in appropriate ways to the equilibrium distribution, which else you would not probably be able to simulate in any other fashion. So that's the concept of a Markov chain Monte Carlo, which is a numerical integration, if you like, for complicated distributions. And this Markov chain Monte Carlo is very important, not only in the field of statistical mechanics, but also, for instance, in financial mathematics, where you want to simulate basically certain probability distributions on the financial market, which are really complicated. So you design a Markov chain that would approximate the solutions. Okay, so that's a long introduction for a relatively short segment, which is about to follow, which at the core has the Ergodic theorem for Markov chains and the statement that aperiodic irreducible Markov chains are in fact mixing, which is also called the Döblin theorem, and here we'll have a very nice probabilistic argument why that is true. So I hope you enjoy the next segment. It's again, in my view, a little bit of a highlight piece of this theory. Okay, welcome to lecture number 7 in our series on lectures on stochastic processes. We will discuss today again the long-term behavior of Markov chains, but now not in terms of recurrence and transients, but in terms of the invariant distributions that we had started to discuss in the last session. In the last session, we were trying to calculate invariant distributions and to see what we can say about recurrence, or how we can connect recurrence and transient behavior to the existence of invariant distributions. And now we want to consider the question in what way we can observe the invariant distributions as really a directly observable quantity. So let us start with an example. Suppose we have the Markov chain here in 2 states. The situation is not entirely symmetric because here we have 2 different probabilities by which the states can make a loop, which means that in case of state 2, the process has probability of 2/3 just to stay in state number 2, and in state number 1 the corresponding probability is 1/2, and as a consequence the probability to make a one-step transition towards 2 from 1 is 1/2, and to make a step from 2 to 1/3 to state number 1 is 1/3. Okay, what's the equilibrium distribution? The condition for being an equilibrium distribution is to be an eigenstate for the adjoint matrix with eigenvalue 1. This is written in 2 sets of equations, instead of 2 equations like this, namely the probability, the total mass of location 1 is the total influx that you have in one step, and the total influx in one step would be half of what is already in 1, that's the influx in the next moment of time, and then you have the influx from 2, which is 1/3 of what was in 2 is now going to 1. So that's the total, if you like, mass balance at the position 1, and the corresponding mass balance at position 2 looks like this. That's a set of 2 equations for 2 unknowns, and the resulting equation, or the resulting solution, is that in the invariant distribution for in location 1 is 2/5, and in location 2 is 3/5. So the fact that the process likes to stay a little longer in position 2, or has higher probability to remain in 2, is expressed in terms of the equilibrium distribution, that the equilibrium distribution at position 2 is higher. Okay, now let's consider some observable of this process, namely assume we take the indicator function of position 1. We start the process in position 1, and we would like to know how that quantity evolves over time. So Zk is the evaluation of this observable on the process, and so it's just the indicator. So in other words, it just in this case counts the number of visits to the state 1, in this case of the chain, and we suppose for a minute that we start the chain in position 1. So, and we take the time average along this realization of the process. So this is the sum of all these counts, which we then divide by the number, or by the time that we spend observing this process. So we have k moments of correction, we have n moments of time on which we do the evaluation. So we count, or we observe the process for n periods of time, and we divide by the total length of this observation period, namely the number of counts. So the number of counts, that's a random quantity, depends on how the path behaves. And in terms of these iterated hitting times, I can compute the number of counts also by saying, okay, that's the maximal amount, that's the maximal index L of these increasing sequence of hitting times whose actual value is still below the number n. So it's just another way of expressing these number of hitting times. Or I could also say it's the number of visits of I before the time n. And if I recall that this sequence of hitting times was formulated in terms of a sequence of waiting times in between the different consecutive visits to the process I, to the state I can also write it like this. It's the maximum number of realizations of these waiting times, such that the sum of these waiting times is less or equal to n. And I want to apply now the strong law of large numbers, which is the classical theory of probability theory, which tells me that sums or mean values, average values of iterated observations of independent realizations of identically distributed random variables converge to the expected value as the number of observation tends to infinity. I want to use this, and I'm having something of a situation like this. So this whole quantity here that appears here on the right hand side is somehow a quantity that involves a sequence of independent identically distributed random variables. And for that I use this fact which we were discussing, I guess, in the second last lecture when we discussed these consecutive hitting times, and we were discussing and we were showing that these sequence of consecutive waiting times for iterated returns to the state are actually independent, which was a consequence of the strong Markov property. So these waiting times in between visits to the state I, iterated visits to the state I, in this case where I is 1, are independent. And the quantity that we're dealing here with is not quite, is a sum of these independent variables, but we don't compute that directly. We want to threshold this number, and basically we take some sort of an inverse function of this number. And for that I will use an abstract lemma now which deals with such a situation, namely, here is it, let psi k be an i.i.d sequence of integer valued random variables, and here I assume that these random variables really assume the values in the integers except 0, so 0 is not appearing, and that's also the case here for these waiting times, because we have really precise, or we have these sharp waiting times, we have the sharp hitting times that we were discussing in this context, which means that the waiting time 0 is not possible. We have at least a waiting time of 1 each time. So therefore we're here dealing with a sequence of i.i.d random variables which assume values in the integers. And then I can consider for each n, I can consider exactly this quantity. I consider the total number of realizations of these random variables. And I can ask myself, given the number n, what's the maximum number of summons of realizations I can take into the sum in order to obtain a number which is still below the threshold n. I can divide this number by the threshold n itself. And the claim here is of this little lemma is that this converges to the inverse of the expected value of this random variable psi when n tends to infinity. Now, assume that we can prove this lemma, then we can apply the lemma to the situation that we have here, where this number of zk variables is written through this transformation in exactly this average threshold numbers. And this tells us then that this sequence of numbers that we have here will converge to the inverse of the waiting times. And this will then ultimately lead us to the following conclusion, which is already here written as a theorem. Namely, let Xn be an irreducible lambda p Markov chain on a finite state space. Then these count this time averaged counts of a visit to the state I, where I is an arbitrary state of my state space, this sequence of random variables converges almost surely to the inverse of the expected return time, of the expected strict return time of that state I. So that's a very intuitive statement. It says that the average value, or the average time average of the number of visits of the chain to a certain state converges almost surely to the inverse of the expected return time. So this is a frequency statement. In a way, what I compute here is an average frequency of visits to the state I. And the statement here says that the average frequency to the state I is exactly the inverse of the waiting time. So it's absolutely intuitive and in perfect analogy with the situation that we would see in a deterministic situation. So the average number of visits to a position in state space converges to the inverse of the expected return time. Okay, that will be the conclusion. And this will be the conclusion once we can convince ourselves that this lemma that I have just formulated is true. So let me say again, the lemma is I have a sequence of independent integer-valued random variables, and I'm asking myself, what's the average number of realizations of this random variable that I maximally can have, which are below a certain threshold n, when I divide this by the threshold n itself. Okay, to convince myself of the correctness of this lemma, let me just first fix a certain integer number k and introduce this sigma k quantity, which is just the sum of the first k realizations. And let lambda n be exactly this number which appears here in the upper part of the page. Namely, for given n, let lambda n be the maximal number of the first L realization of these random variables psi j, which are still below the threshold n. Now, if I insert as threshold value n exactly the number that I get when I sum up the first k realizations, then I exactly obtain this number k, because it's just exactly this k number of realizations that I can use to fill up this number. So this is a deterministic statement. It's just about saying, okay, so how many numbers do I need? How many of real numbers, how many non-negative numbers of a specific type, of specific value can I sum up if they are non-negative to obtain exactly the number, the total sum of the first k variables? Okay, so that's exactly k. Here is nothing spectacular, but the important or relevant consequence of this is the following, so that if I take the ratio of this lambda quantity at the index value n equals sigma k, and I divide by the same index value, which is then sigma k, then I can also multiply and divide the same expression by k. This doesn't change anything. But by this identity, which is above here, I have just convinced myself that lambda times sigma k is k. So I have a cancellation of this part here against the k here, and what I obtain in the end is a k over sigma k. But k over sigma k is now the inverse of sigma k over k, and sigma k is the sum of these first k random variables, which are independent. So this is now a situation to which I can apply the straightforward law of large numbers in its strong form. So the strong law of large numbers tells me that this ratio of numbers converges to the inverse of the expected value of the random variable psi1, say. Okay, so that would settle the situation, or which would settle the question in case when these so the statement here that is to be proved deals with the sequence lambda n over n. And what I have just convinced myself of is the case that this conversion is correct if I choose n, a subsequence n, namely the subsequence n is equal to sigma k. Now for a real n sequence, since the sigma k's are increasing, I can find a sequence kn such that in fact sigma kn divided by n tends to 1, and such that this n for the properly chosen kn lies between sigma kn minus 1 and sigma kn. And then this ratio by the monotonicity of the lambda expression is simply bounded from above and from below by these two expressions, by the corresponding ratios, when the n index is replaced by sigma kn minus 1 or sigma k. And if I look at one of those, like lambda over sigma kn divided by n, then I can again multiply and divide this expression by sigma kn alone. And I have just had before that this lambda sigma kn over sigma kn, this converges to the number that is in the claim, namely the inverse of the expected value of psi. And it remains this term sigma kn over n. But if the kn sequence is chosen, as I had just said before, that each n is squeezed in between such sigma kn minus 1 and sigma kn, then this will converge to 1 for n tending to infinity. So in the end, by this sandwiching of the actual quantity I want to study between these two different quantities, which I can understand, I will ultimately see that I in fact do have the claimed limiting behavior. Okay, and this way we have already proved our first theorem in today's session, namely if xn is an irreducible lambda p Markov chain on a countable state space S, then we have almost surely, as I just said, that the mean number of visits, so if you like, the average frequency of visits to the state I converges almost surely to the inverse of the expected return time when the time window of observation tends to infinity. So here we have a first instance of what I said in the introduction, that is a theorem which shows that a time averaged quantity, which is still dependent on randomness, converges eventually to a deterministic quantity, which in some way is a quantity which just depends on a spatial quantity, on a spatial feature. This 1 over ei over tau I plus this expected return time, the inverse of that, was exactly the value of the invariant distribution for a positive recurrent Markov chain. There we saw in the previous session that this is exactly the invariant distribution. Okay, we can now make one little step to generalize this a little bit, to have the full Ergodic theorem for Markov chains, which is a modest reformulation of the previous just obtained result, but which is probably even simpler to formulate and nicer to state. The Ergodic theorem for Markov chains goes as follows. So let X be an irreducible positive recurrent Markov chain with a countable state space. then for all bounded functions which are observables on state space, we find that the time-averaged evaluation of the process of the observable along a trajectory, along any trajectory, will converge almost surely, so that means for almost every trajectory, will converge to an average quantity of the observable, where we take the average of the observable on state space with regards to the invariant distribution of this Markov chain. So on the left-hand side, you have a time average quantity, and the time averaging here is time averaging along one fixed trajectory of the process. And on the right-hand side, you have a spatial average of the function of the observable, where you take the average with respect to all possible states in the state space. So in this regard, it's quite a powerful theorem. It says that the long-term behavior of the observable along effectively any trajectory on which you sit will eventually be a quantity which depends just on the function f on the entire state space when you evaluate that with respect to the invariant distribution of the process. Okay, how do we prove this? Well, okay, let's assume first that the function has finite support, which means that the function is zero outside a finite set, or which we also can formulate like this. The function is the same as if I multiply the function with an indicator function for a certain subset of states A, which is assumed to be finite in cardinality. Then the evaluation of the trajectory by means of this observable f is nothing but a linear combination of evaluations or hitting time counts for sets A in the subset A, where each of these hitting time or hitting counts is multiplied by a certain coefficient f alpha, which is actually the value of the observable f on that state. Here I have used nothing but the fact that a function which has support on a finite set is effectively just a finite linear combination of indicator functions for the one-point sets which correspond to the individual elements of the finite set A. But now I can interchange, if you like, the summation with respect to time parameter and with respect to the states A in the set A. And to each of these individual A sets, which is a finite sum, I can apply the previous argument, which we had just done in the previous page, which was relying on the law of large numbers, to convince myself that this linear combination of visit counts will then converge to the corresponding linear combination of pi values, where pi is the invariant distribution of my Markov chain. And this, of course, I can also write as the corresponding integral or inner product of the function f against the invariant distribution pi. So for finitely supported functions f, this is in fact the direct consequence of the previous theorem. And for not finitely supported functions, I can use the fact that f is bounded and continuity of the probability measure pi by finite exhaustions to convince myself that for a certain error threshold epsilon, I can find some finite set which exhausts the set S up to precision epsilon with regards to the measure pi. This is just continuity of measure, if you like, or the fact that this possibly infinite sum, which is finite, can be approximated by a finite sum with arbitrary good precision. Now let us introduce the notation pi n for what we could sometimes call the empirical time average distribution of the process K. So at position I, and this pi n I is just exactly this mean visit frequency. So then this pi n, if I understand this as a vector or as a function on state space, this again realizes a probability measure, and then this evaluation of the function f along the trajectory can also be understood as the integral, if you want, of the function f against this empirical counting measure. And ultimately, the claim then, which I want to prove, is that this integral against this empirical counting measure of the function f is the same, or it converges to the actual, so what I want to prove is that this difference, which is the difference of the integral of f against this empirical counting measure, will converge to the average of f with respect to the invariant measure. And before I do that, I want to control one of the errors that appears in this error decomposition that I shall do in the next slide, or the next moment. Namely, let us now understand what's the error that I make on the level of the pi n function if I replace the integral of f with the integral of the cutoff version of f. Now, by construction, this is effectively only the integral of f with regards to pi n on the complement of a. So, and by the boundedness of f, this can be estimated by the supremum norm of f times the pi n measure of a complement. But pi n is a probability measure, so the pi n of the complement is 1 minus pi n of a. A is again now a finite set, and on the finite set I have an approximation of pi n by pi. So therefore, for large enough n, this 1 minus pi n of a is estimated from above by 1 minus pi plus epsilon, because pi of a and pi n of a differ at most by, say, epsilon if n is sufficiently large. But this difference here of 1 minus pi a is epsilon at most by construction of a, so the whole thing is no bigger than the infinity norm of f times 2 epsilon. And so I can use this now for the full error analysis. Here with the triangle inequality, namely, I want to convince myself that this difference becomes small, and for that I replace in both expressions the f by the corresponding cutoff version of f, and then I compare, and because I can use the previous result to convince myself of the convergence of these two integrals against pi n and pi if the function of which needs to be integrated is of finite support. So this part here is the middle part of this triangle error decomposition, which I had understood already, and so what remains is the relative of the error that I do each time I replace in each of these integrals the function f by the corresponding cutoff function. This is one of the two errors, and this is the second error, and the first error appears with respect to pi n and the other with pi. And the first error is just the one that the first of these three is just the one that I had just discussed above. It was estimated by 2 times the infinity norm of f times epsilon. This term here is the term which clearly goes to 0 for n to infinity by the previous findings. And the other term here is again by the choice of the subset A is less or equal than the infinity norm of f times epsilon. So therefore I can conclude that I have this type of convergence, and the Ergodic theorem for Markov chains is proved. So let me give you the statement again. If X is an irreducible positive recurrent Markov chain, Then for all bounded measurable functions, measurable is always the case here because we're talking of a discrete situation. Then for all bounded functions, the time averaged observation of the process, of the trajectory, by means of the observable f, will lead to the average value of f when taken with respect to the invariant distribution pi. I probably should note one difference here towards straightforward application of central limit theorem. These random variables which appear here are not independent because the Markov process, each states of the Markov process are not independent. The jumps are independent in a way, but not the actual realizations. So of course there is independence here somewhere around, but it's not so trivial to extract the independence in order to apply the central limit, the law of large numbers. And we did it effectively. We did effectively introduce independence here by going back to these consecutive waiting times, which are chosen in such a way that each time I register a new visit to the state I, here say, I reset the clock and I can restart the Markov chain without any change of the distribution or of the statistical properties. And this is where the independence comes in. So sometimes people call this sequence of visiting times, or the sequence of hitting times, which we had introduced 2 lectures before and which are appearing here as well, they call it renewal times, which is intuitive because it says that the process is kind of started afresh. Everything in the past that happened in the past is forgotten, and we start the process afresh, basically in the same way as we had started the round before. And this is where the independence here is extracted, and which then is used here in this argument for the Ergodic theorem. So we see in fact that this invariant distribution pi, which we introduced in the lectures before, just by requiring that there should be some statistical distribution on the collection of states, which should be stable, which should not change over time. We see now that this equilibrium distribution actually is attained. And you should also note that this statement here of the Ergodic theorem did not make any assumption of whatsoever on the initial distribution of the state, of the initial distribution of the chain. In fact, in the argument here, I should probably also mention this, in the argument we did here before, we were assuming that these waiting times are all the same and all identically distributed. And this was made for the case when we start the process in that state I, where we want to reset the clock each time. And as a matter of fact, if we start the process in some other state, then we just wait a little until we first hit that state I and then do the process. So if you start from another, but the Dirac distribution in that state, all that changes is just the distribution of the very first waiting time. And after that, the whole argument is exactly as before. And since all this deals with average values of infinite sums, limits of them, it is completely irrelevant what quantity you put at the first place in this sum, because by this 1 over n averaging, and as n tends to infinity, the first entry is completely cancelled or neglected. Fine. So that's the Ergodic theorem for Markov chains, and we can ask: is that all? Can we say something more? And yes, of course we can. Else I wouldn't ask this question at this level. Let us namely consider now the following Markov chain, two-state Markov chain, which is in fact deterministic, but as such it is still a Markov chain. Because it's memoryless, namely it's a Markov chain in two states, and we have just a rotation. At each moment of time, I switch from the current state to the other one, and vice versa. So the whole thing is just a rotation in these two states. Of course, the invariant distribution here is 1/2 and 1/2. In terms of counts now, that's kind of easy. The half of its time, wherever you started, the process spends in state 1 and half of its time in the other state. So therefore, obviously, that's the invariant distribution. That's, again, the Ergodic theorem here, which is applicable. But we could ask ourselves, what's the distribution of the state after one step or after n steps? So let's assume that we start the process here, this deterministic process, but still a full justifiable and full straightforward Markov chain. Let us assume we start the process now in state 1 again. Consider the observable, which is the indicator function for the state 1. And then we can ask ourselves, what's the expectation of this observable as time evolves? At each moment of time, we evaluate the expectation of this observable of the process, or yes. And so we see that since it's an indicator function, in particular, and we have here a deterministic situation, this expected value is in fact just an evaluation of this rotating process. And it means that in even moments of time, we are back in 1, which produces on the indicator a 1, and at odd times we are in 0. And so we see that although the process is ergodic, so the time averages of these numbers, they converge reasonably to what we expect. The observation of a single time point alone, so of a sequence of single time points alone, does not lead to any convergence. So in that regard, the process is still pretty unstable. It's true that if I take average values along trajectories, the process produces these statistical averages, which are valuable. But if I evaluate only the process without averaging, but just I observe the sequence of evaluations independent of other time points, so I observe them only one time point after the other, I see no convergence at all. But on the other hand, I would expect such a thing, at least in some situations. And that's now the concept of mixing, which I shall introduce, which is also a standard in classical notation. Namely, I call a Markov chain, or better, I call the corresponding transition matrix mixing on this collection of states as if the iterated application of the adjoint matrix P star applied to any initial distribution lambda converges to the invariant distribution mu. If that's the case, then I call my Markov chain mixing. Now, in the situation above that we had here with this rotation dynamics on two states, I did not have this mixing property because evaluation of, so this expression here, I can also write in terms of my linear algebra fashion kind of writing. I can also write this, if you remember, as the integral of my starting distribution, which is delta 1 in this case, times the iterated application of the Markov transition of P to F. And then this is, of course, the same as if I apply the adjoint matrix in kth power to the Dirac distribution in 1 and then apply to F. And so this term here, this expectation here, was just there, evaluated, and I had seen that this gives me an alternating sum, an alternating sequence, and I do not have any kind of convergence here. So therefore, in particular, these iterated applications of the adjoint do not converge to anything. Here in the case when lambda is chosen to be the Dirac delta function in state 1, say. But still, I could hope for such a property. I could hope that if I take an observable f and I evaluate the observable along the Markov chain, and I do not do any averaging with respect to the Markov, with respect to the time, but I do at each moment of time, I do some averaging with respect to the distribution of the chain at that moment. Then I could hope that this still converges. This would tell me that the distribution of the Markov chain converges, in fact, to the invariant distribution. That's exactly what it says, independent of the initial distribution. Okay, and there is a theorem which I shall now present, which tells us under what conditions it gives us sufficient conditions for a Markov chain to be mixing. And this is the contents of the next part. So the proof that I shall present, or the theorem that I shall present, is the Döblin theorem, as it is called, on mixing of Markov chains. It's a generalization of a theorem which is called the Perron-Frobenius theorem in linear algebra, or in numerical analysis. There you use it typically for the situation of matrices, of finite matrices. But recall that here in the world of Markov chains with finite correction, with countable state spaces, basically we're doing something like linear algebra in infinite dimensions. And this Döblin theorem is an extension of this Perron-Frobenius theorem to the case of an infinite dimensional index set, if you like, or index space. Okay, and the core concept here is the concept of periodicity. Here is the definition of periodicity of a state. So let I be a fixed arbitrary state. Then you can consider all the powers of the matrix P, the transition matrix, which are so that they allow for a positive transition in that corresponding number of steps from the state I to itself. So that's the total collection of lengths of cycles which start in I and end in I, which have positive probabilities. It's the cycle lengths. Yeah. So this collection of L numbers is the collection of all cycle lengths which can occur with positive probability and which lead from I to I. And the greatest common divisor of this collection of L values is what I call the period or the periodicity of the state I. So it's kind of clear what this means. So suppose you have a chain that can do a certain number of steps, and then I have a minimal sized circle which I can do, and I have all kinds of possible circles which are possibly collections and which are composed of certain sub-arcs of these circles. And the greatest common divisor of all these circles is called the periodicity or period of this. And I call this state aperiodic if the greatest common divisor is 1. So if they are relatively prime, these numbers. And then there is a simple remark, which I shall put as an exercise, that this periodicity, so this greatest common divisor, is the same for all states which are in the same irreducible class. So recall that we said two states are in the same irreducible class if there is a finite length positive probability to go from one state to the other and vice versa. And here we make the claim that the periodicity, this greatest common divisor of these possible circle lengths, that this is shared among all the states of the same irreducible class. And the Döblin theorem deals with the case that we are having an irreducible chain, so we have one periodicity number, and that is 1. which is the so-called aperiodic case. So we say, or the statement of the Döblin theorem then is that if P is a positive recurrent, irreducible, and aperiodic transition matrix, then this transition matrix is in fact mixing. By the way, the previous example that we had about this rotating system in two states, this is obviously a two-periodic Markov chain. So it is recurrent, it is positive recurrent, it is irreducible, but it is not aperiodic, because here the period of this, or periodicity of this chain, is obviously 2. It's not a situation in where the Döblin theorem applies, which is of course consistent with our finding that this is not a mixing chain. Again, let me tell you that, or let me say again, that in case when the state space is finite, then this is a statement about existence in a way, or it's a numerical statement about how to compute this eigenvalue, the eigenstate or the eigenvector for the adjoint of the matrix, in case we have a stochastic matrix which satisfies these aperiodicity and irreducibility constraint. In this case, this Perron-Frobenius theorem gives us a iterative scheme, in fact, how to compute this invariant distribution. Namely, we just take the adjoint of the matrix, we feed the matrix with any kind of initial distribution, any initial vector, and then we iterate this matrix and apply it to the initial distribution lambda, and then the theorem tells us that these iterates, in fact, converge to a vector which is then the invariant distribution of this matrix. That's exactly the contents of the Perron-Frobenius theorem, which is a theorem from numerical linear algebra, where you might have seen it, probably. And here, the proof that we shall give here will be probably different from the one that you might have seen in your numerical linear algebra class, because it uses a very fancy and very, very neat probabilistic argument that I shall present to you now. Okay, the proof relies on one lemma from, if you like, elementary number theory, and I shall not give you this lemma. You may find the lemma in the literature. I might just, you can look it up in the book by Norris. It says the following: if you have a subset of the integers whose greatest common divisor is 1, and which is closed under addition, namely if you take two such numbers which are in the set L, L1 and L2, which are in the set, then the set that you consider is supposed to be so that also the sum of these two numbers will also be an A. So we say A is closed under addition. So again, let me say it again. If I have a number L1 in A and L2 in A, then the sum should also be in A. Then, that's the conclusion of this lemma, there exists a certain integer L such that all numbers from that integer L on will also be in A. So in other words, if you have a subset of the integers whose greatest common divisor is 1 and which is closed under addition, then this set must contain a half line. Okay, this is a lemma from elementary number theory, which I shall not prove to you, but we will use that in the following fancy probabilistic argument. So I want to prove at first that for two arbitrary initial positions, for two arbitrary initial measures, this sequence of iterates of the adjoint of the matrix to these arbitrary initial measures will converge to one another. And then in the second step, if I choose not any arbitrary measure from the second side, but the invariant measure, then I obtain this convergence statement. That is the claim of the theorem. Okay, and we start by considering the case that the two measures which I have chosen as starting measure are Dirac delta functions in two positions I and j. And we take two independent copies of Markov chains, of our Markov chain, where one is starting in position I and the other in j, where I and j are arbitrary. And we want to consider the case when the two are constructed and chosen to be independent. We know how to construct an arbitrary Markov chain with p and lambda on one state, and we can construct it on this canonical path space, and we can take another path space and take another construction of the y process, and then we take just the product of these two spaces, and this will then be a construction of two independent processes. Okay, so we have these two independent processes which have different starting points, and we select at random a fixed some point in state space which we call S. Okay, doesn't matter for the argument what states S we choose. And we define tau to be the first time, which is now to be considered to be a time on this joint path space. So it's an evaluation which evaluates the two paths x and y, and it will be the first time when the two paths meet, and the two processes meet, and they should meet, say, in the state S for simplicity. You could think of more complicated definitions or more generous definitions, but we want them to meet. We want them to meet, and we want them to meet not anywhere but, say, in the state S. And then the central claim of the whole argument is that this meeting time, this tau, is finite almost surely. Okay, we prove this in a kind of indirect fashion, and then once this proof is done, then the rest will be easy. Okay, in order to convince ourselves that this hitting of these two processes appears with infinite time almost surely, we consider this stochastic process which is obtained by looking at the two processes simultaneously, which are independent. This would be a process which can be thought of as a process on the Cartesian product of the path spaces. So it will be a path in two variables, and it will have as a starting distribution, if you like, the product measure of the two Dirac distributions, and its transition matrix will be now a transition matrix in the double number of coordinates. Namely, we will have now transitions from state pairs k prime to state pairs l prime, and the probability of these transitions by independence will be just the corresponding product of the individual transitions, namely from k to l and from k prime to l prime. These are now the transition probabilities for this new process, which is doubled in number of coordinates, and therefore we have a slightly more complicated transition matrix structure, which here is still easy because it's just a product. The claim here is now that this new process in double variables is again an irreducible and positive recurrent process in this squared state space. Okay, why is it irreducible? And here will be the point where we apply this number theoretic lemma. So first of all, we use the irreducibility of each of the individual chains in order to convince ourselves that if we fix a pair of pairs for transition, so we ask for transition from k to l and k prime to l prime, for arbitrary pairs kk prime and ll prime, and that should be possible with positive probability for a properly chosen number of time steps and steps. Okay, first of all, so we have now these two pairs which induce requested transitions in the corresponding coordinates from k to l and k prime to l prime. The irreducibility of the chain x on y respectively tells us that there exist certain numbers n and m such that these transitions alone for possibly different n and m can happen with positive probability. Now, again, if you like, by recurrence of the corresponding states L and L prime, this I have positive numbers A and B, or for any positive number A and B, such that these simple loops from L to itself and from L prime to L prime, that this happens with positive probability. I do have such numbers A and B. And moreover, the collection of all those numbers A and B, each individually, are exactly, by our aperiodicity assumption, are exactly of the type that I can apply this number theoretic lemma, which tells me that there is certain half planes, if you like, half lines as powers of the matrix, which produce strictly positive probability for all possible numbers A and B, provided they are big enough, namely bigger than the left hand, if you like, boundary point of the first half line, which is the number L1, and greater or equal than the boundary of the second half line, which corresponds to this greatest common divisor set. So basically the set of powers which produce positive LL probability. By the way, here is a misprint in my notes, which I can correct easily. So I want that this transitions from L to L here are positive, have positive probability, and the transitions here from L prime to L prime have positive probability. So that's the right way to put it. Okay, let me say it again. By the number theoretic lemma, I know that there's whole ranges of integers A and B, such that in fact these loop probabilities are strictly positive. And therefore I have a whole half line which starts at some minimum value, which is n plus L1, when all these numbers here become positive, and I have a half line of numbers which starts, for instance, with m plus L2 of numbers where these powers are all positive. So therefore, at the maximum of these two numbers, I'm in both of these half lines. In particular, I'm in both of these sets. So for t equals this maximum of these 2 points, I have that this joint t power is positive for these two transitions. And here again is a little misprint, because here I want to have a k prime here. Okay. And in particular, I have convinced myself now that this chain in these doubled variables is in fact irreducible, because for every possible pair kk prime to ll prime, I have found some power such that this transition is positive. That gives justification for the claim that the chain is irreducible, and the positive recurrence can be checked, as we know, by giving a probability distribution, invariant distribution, a probability distribution of the collection of states which is invariant, And the choice I do here is obviously the tensor product of the two invariant distributions, of two copies of the invariant distribution in these two variables, namely the tensor product of mu with itself, where mu is the equilibrium distribution of P. Then the adjoint of the tensor product of these two matrices is just the tensor product of the adjoints. If I apply this to a tensor product of vectors, then this is just the same as if I apply each of these individual matrices to the two respective vectors and take the tensor product then. But each of those products just by invariance gives me the mu vector. So therefore I'm ending up with mu tensor mu again, which is what I started with. So in fact, mu tensor mu is invariant, and it's a probability distribution as one checks easily, obviously. So in particular, it's summable, and therefore the chain is positive recurrent. So positive recurrence implies, of course, that the expected return time, the expected strict return time for any state is finite. So in particular for diagonal states. And since this whole chain is irreducible, I can also make the same statement of finite hitting time for an arbitrary initial distribution, which tells me that for starting distribution concentrated in the pair of points I and j, which is just one of all those possible starting distributions, I will also find that I have a finite hitting time of this diagonal state SS, which in particular means that this tau time, which is this hitting time, is finite, almost surely under the probability measure which I consider, namely the probability measure associated to starting in positions I and j. Okay, so therefore this tau time is in fact finite, almost surely. Good. And now comes the conclusion using the stopping time by the following ingenious construction, which is called a coupling construction. Namely, I will consider now a third Markov chain, which is something like, when I present this, I call it the bug process. So you have two cats, if you like. You have the X cat and you have the Y cat. So both cats, if you like, they walk on state space and they have their transition probability. And now we introduce the bug. So we have the cat, and the bug. And the bug does the following. The bug is the Z process. It's the location of the bug. And the bug starts on the X cat. So it's brought to life, if you like, on the X cat. And it travels with the X cat until the first time that the X cat and the Y cat meet in position S. And then the bug makes a jump when the two cats sit on the same spot and jumps onto the back of the Y cat. And from now on, travels with the Y cat. So the bug changes its horse, if you like, which in this case is not a horse but a cat. And it can change the horse only when the horses are on the same spot. Well, but if you forget about the underlying cats and look at the dynamics of the bug alone, the bug never makes a decision on its own. It just follows the decision that the respective bug or the respective cat is currently doing. So once it made its choice regarding on which back it is sitting, it will just be the slave of the underlying cat. So, and in particular, its decisions will be completely governed, and therefore will be also a Markov chain. And we see immediately that this bug as a Markov chain alone is again a Markov chain which follows the transition probability P, but which started with the same distribution as the X cat, namely in position I. Okay. Now you will see why this bug process is so valuable. Now we want to evaluate ultimately the difference of the two distributions that we obtain by iterating the P star matrix on these two different initial distributions, delta in I and delta in J. If we write out these two linear algebra quantities in probabilistic terms, if you like, this is the first is the probability, right, and we evaluate these two different distributions in the state U, say. U is another state from the state space. Now we write these two quantities in probabilistic fashion, and then the one is the probability that the x cat is in U, and the other is the probability that the y cat is also in U, exactly, but the x and the y cat were starting in different positions. But since one second. All right. So in distribution, right? Sorry. In distribution, the x process and the z process are the same. Regarding the probability to be there or not, this is just a probability regarding the statistics of the process. So it's just a question, if you like, on the lambda and p thing. And this is the same as if we had discussed the bug, because it started with the x cat. But the probability whether or not the bug is in U can be decomposed according to whether the transition of the bug had appeared already or not. So this location of the bug process, let me say it again, is now decomposed into the question whether the time k was prior to the meeting time or after. Now, if the meeting time was prior, if the if the time when you do that is at the time when the meeting hasn't yet happened, then the bug process is exactly the x process. But here, if the meeting time had already passed, so k is greater than the meeting time, then the bug process is the y cat. And so we see that this probability here is a probability which involves the y cat, and here is the y cat alone, and we can see that there's a partial cancellation of the two probabilities here, namely what remains is the probability for the y process to be in U, and that the k, the moment of time k, is prior to the meeting time. This is the complementary condition which remains after I evaluate here this sum. And I have two events which are both sub-events of the event that the time k is prior to the meeting time tau. So therefore the difference of these measures of these two sub-events is in particular bounded from above by the measure of the event alone. And this is now the event that k is less or equal than tau. But if I let k tend to infinity, this converges, if you like, to the probability that tau is greater or equal to infinity, which is not the case, which has a probability 0. So therefore the whole thing, by continuity of measure, converges to 0 as a consequence of the previous finding that this meeting time is finite almost surely. This tells me that the process forgets what its initial distribution was. So for all initial distributions, different initial distributions, the distributions converge to the same limit point, and we have one distribution which will not change over time, which is the invariant distribution. So therefore all distributions under the iterates of this P star will converge exactly to that invariant distribution. I want to conclude with two applications, one in physics and one, if you like, in optimization. I wanted to say that, as I had announced, these two results are interesting from a Markov chain perspective, but they are also good for applications. Namely, sometimes you want you do start not with the Markov chain and ask for invariant distribution, but sometimes you do the other way around. You start with a certain distribution on states, and then you want to ask for a Markov chain that realizes this distribution in the limit. And one example is this Ising model of statistical physics, where you have the collection of states will be the collection of all plus or minus pictures on a certain grid. That's a state. So all possible plus or minus, so you can fill the grid with pluses or minus, or green or not green if you like, which you indicate by +1 or -1. Then you have a notion of an energy for such a picture. So here it's like a collection of black and white pictures on a certain resolution, and you count the numbers of coincidences between adjacent patches. This is what gives rise to this magnetic energy, and then the corresponding exponential measure, which is this one here, is the so-called Gibbs distribution for this energy function. And when you do this number of possible patches, when you let this tend to infinity, then this is what you call the thermodynamic limit. That's a very interesting model, although it's very simple at the beginning. And it turns out that it's very difficult to sample from this distribution, just to generate realizations. So basically what this Gibbs distribution gives you is a probability measure on the collection of all those possible images. Right? So you have these black and white images. Each image has a certain energy, which is measured in terms of this energy function. And then you introduce a probability distribution which tells you that images with high energy are less likely in an exponential regime than images with low energy. It's actually pretty complicated distribution, and it's difficult to generate random images according to this distribution. And what you do is you set up a Markov chain which is mixing and which has this invariant distribution, has this Gibbs distribution as its invariant distribution. And here is this so-called Metropolis sampler, which does this. And it's a Markov chain which is designed to generate, if you observe it long enough, which is supposed to generate random images according to this Gibbs distribution. Because direct sampling from this Gibbs distribution is basically impossible on a computer. So if you like, you start with a completely white picture, and then you let the process evolve according to this, what is called the Metropolis transition kernel. And since this is a mixing and positive recurrent and invariant correction aperiodic kernel, you have a guarantee that in the long run this process converges to this Gibbs distribution in law. And an application in optimization is when you have a certain number of possibilities or states for a certain optimization problem, and you have a function phi, and you want to find the minimizer of phi on the collection of states, you do a similar thing. You write down the corresponding Gibbs distribution, and then you consider the Metropolis algorithm, which samples according to the Gibbs distribution. But the Gibbs distribution gives more energy or gives more probability to states with low values of phi. So therefore, this Gibbs distribution concentrates on those minimizers that you look for. And the Metropolis the simulated annealing algorithm is now an algorithm which turns up the parameter beta, which is the weighting parameter in front of this energy function, to make this preference for low energy functions, for low energy positions higher and higher. And then there is a theorem which tells you that if you cool down the system according to this beta k, which in this case means that you have to send beta k to infinity, but not too fast, so it should not go quicker than logarithmically in a way to infinity. If you then consider this sequence of realizations of this chain for this now changed over time temperature parameters beta, then you have convergence towards the uniform law of the minimizers of phi. We shall do this in the exercise a little later, or I will discuss this in the next session a little bit. This is an important and very interesting application of Markov chains to the case, or to the field of optimization. And it uses again this property of mixing and convergence to the given distribution, which here in these two examples was the starting point. So you have a starting point, which is a probability distribution on certain possibilities, and you want to generate a Markov chain in order to have realizations according to this law.